So we said that the next chunk of the class that we're going to deal with is going to be dealing with circuits. So hopefully you guys have already watched a video introducing the basic circuit elements that we're going to look at. Now let's come back and sort of continue this introduction to circuits in terms of some basic circuit concepts. So fundamentally, what is it that we're going to keep track of when we're dealing with circuit problems? And there's basically two things. One is we're going to keep track of energy. We're going to choose to do it as energy per charge, which means that we're going to keep track of the potential. Okay. So we'll see that there's an advantage in this because in keeping track of the energy per charge, it means that we don't really care what the charge carriers are that are moving around in our circuits. And we'll talk about why that's actually a useful thing. And then the other thing that we'll keep track of in circuits is the charge itself. And we'll do that by keeping track of what's known as the current. So fundamentally, what is current? It's the rate of flow of charge in a wire, which is just a fancy way of saying that if you were to stand there and watch a particular spot within your circuit, you would watch some amount of charge flow by within some amount of time. So this is no different from talking about the current of a river, right? You watch some amount of water flow by in a certain amount of time. It's just that the current that we're interested in within our circuits is a charge current. So we're going to calculate that. I is the letter that we're going to use to denote the current. And then we calculate the current by talking about the amount of charge that has flown past in some amount of time. So we're going to take the charge per time to calculate the current. So if we think about units, well, this tells us that the units of current is going to be units of charge, that's coulomb, divided by units of time, that's seconds. So our SI unit for current is coulombs per second, which is also known as the ampere. So how do we create currents in a wire? And you guys will know that when we talked about electrostatics, we said the electric field is zero inside a conductor. Our charges will move around to ensure that and they'll move around on the outside of the conductor to ensure that the electric field inside of it is zero. That's what it means for a conductor to be in electrostatic equilibrium. Well, basically, if we're going to have current flowing around, that means we need to have a steady flow of charges. In order to do that, we have to maintain a steady force acting on them. So something has to push those charges around. And the most obvious way to push those charges around, and not the only one, is to create an electric field. So what we'll do, or one way we'll sort of start in dealing with charges, is basically we'll say that the charges are arranging themselves on the surface in such a way that it creates an electric field inside the conductor. That's what's going to push charges around. Now, I mentioned before that we're going to keep track of the potential, which means the energy per charge, so I don't really care whether these charges are positive or negative, and that ends up being useful because for most things, right, if you set up a simple circuit, what's actually flowing is the electrons. Electrons are negatively charged. We're going to pretend that the direction of the current is in the direction that positive charges would flow within the electric field. So here we have an electric field that's pointing to the right. Positive charges would feel an electric force pointing to the right. They would move to the right. So we're gonna let that be the direction of current flow. There are situations, say when you're dealing with ions within a fluid, where you will actually have both positive and negative charges moving around. But most of the time, it's actually negative charges that are moving. And this, again, is one of those things where we have Benjamin Franklin to blame because his assumption was that the charge carriers, when we were talking about current, were positively charged, right, not negatively charged. And, he happened to be wrong. The upside is that it doesn't matter whether he's right or wrong. We can go ahead and use this convention about the direction of current, and it won't cause us any problems. So we're going to assume the current flows in the way positive charge would flow within the circuit. So how do we keep track of energy and charge? And there's a couple of rules that we're going to use, and they're known as Kirchhoff's rules. One of them is the loop rule. And the loop rule tells you that the sum of the potential differences across all the elements around any closed loop must be zero. So mathematically we write this as the sum of the potential changes around a closed loop has to be zero. So you'll notice here's a simple circuit. It has a battery. That battery has some voltage. It's providing a potential difference. Here are all of our wires. They're connected to 1, 2, 3 resistors. And so what happens when we think about the loop rule is basically it says, well, pick some closed loop. So we'll start from this point. We'll go across the battery from the negative terminal to the positive terminal. We'll come across this resistor. We'll come across this resistor. We'll end up back where we started. So that's a closed loop. So what Kirchhoff's loop rule tells us is, well, we know that when we go from the negative to the positive terminal of the battery, that we're going to have a potential increase. Right? So again, this is my think in terms of what we know about negative and positive charges, right? If this is, say, a negatively charged plate, that's a positively charged plate, my electric field would point from the positive to the negative, and I'm moving against the electric field, which means I have to be increasing the potential. So when you step from the negative to the positive terminal of the battery, and the negative is the shorter line, the positive terminal is the longer line, you increase the potential going in that direction. So this is a potential increase. Well, because this is a ideal wire, there's no resistance within this wire, which means that the potential here has to be the same as the potential at the positive terminal of the battery. And now as I walk across this resistor, I have to have a potential drop. So some of the energy is being used up as I come across this resistor. I'm left with whatever this potential value is. It's going to be the same until I reach the other resistor, and then again I've got to lose energy in the form of potential, so I'll have another potential drop as I cross this resistor that gets me back to basically the same potential as the negative terminal of the battery. So I can do this for any particular loop, right? So I did it for this loop and saw that the potential increase across the battery had to be equal to the potential drops across these two resistors. If I pick a different loop, right, start from the same point, I still see the same thing. So again, I'm going to have a potential gain across the battery. I'm going to have a potential drop across this resistor and a potential drop across this resistor. And the drop across these two resistors has to be the same as what I gained across the battery, because I've come back to the same point I started. So the potential changes through my whole loop have got to add up to be zero. We could pick a loop without the battery. So again, we could start up here at this point. And again, we would go across this resistor. We would go across this resistor. And the way this works out is we'd be going across this resistor with the current. That's going to be a potential drop. We're going to go across this resistor against the current. That's actually a potential increase. And so this tells us that the potential drop across this resistor has got to be the same as the potential increase across this one in order for our loop rule to hold. And so this is what we'll do to use the loop rule. Really, it's just a statement of conservation of energy. Right? It's saying that whatever energy you gain here will be lost here. Our second Kirchhoff rule is known as the junction rule. So let's start by defining what a junction is. And so a junction or a node is just a way of saying you've got a point where the wires split, and so current can flow in a couple of different directions, right? To anthropomorphize it, we'll say, oh, the current has a choice. Right? It could go this way or it could go this way. What the junction rule tells us is the sum of all the currents entering the junction has got to be the same as the current leaving the junction. So we'll often write this as the current in has got to be equal to the current out for each junction. And so here in our simple circuit, what we'll see is the current will come in from the battery, and again sort of how we know this is what the current is doing is part of what will develop over the next couple of weeks. So if this is not intuitively obvious at the moment, don't panic. This is part of what we'll be working on and learning. But what the junction rule tells us is that the current that's coming in, so current comes out of the battery here, comes in to this particular junction, it's going to go out. Some of it will come out this way. The rest of it has got to come out this way. And so this means that the sum of these two, the currents flowing out of that junction, has got to be equal to the current that flowed in. Right? If I think about my second node or my second junction here in the circuit, again, if I watch this current, it's going to come all the way around and flow in. This current will flow down across this first resistor and flow into this junction, and then they will recombine and flow back out and flow back into the battery. So again, these two have to sum up to be exactly the same as this one. So all we've done in talking about this junction versus this junction is switch whether we've got two currents coming into the junction or two currents going out of the junction. Everything else mathematically has got to be exactly the same. Our junction rule is really a statement of conservation of charge. It's basically pointing out that all the charges that come into the junction have got to leave. We're not building up any charges here. So charge has to be conserved within the circuit. So what are the two things that we're keeping track of within a circuit? We said we're keeping track of energy through the potential, and we do that through the loop rule. And we're keeping track of charges through thinking about the currents, and we do that with the junction rule. So the last thing to sort of go ahead and lay out up front, because we'll be talking about this a lot, is how we choose to connect elements. And there are two basic ways that we can connect two elements. So again, I don't care what kind of elements these are. They can be any of the ones that we've talked about. But you notice here that what I have is I have a wire and an element, a wire, an element, a wire. So what this says is whatever charges are coming through, and they go through element 1, they have to go through element 2 because there's nowhere else for them to go. So one of the things this highlights is you don't lose charge within an element. Right? You lose energy. You may lose energy, so the potential may decrease across the element, but you don't lose charge. So whatever charge comes into the element has to go out of the element. And in this case, the way I have these two connected, which is known as in series, all the charges that come in this side through element 1 have to leave element 1, and they've got no place else to go but through element 2. So for elements connected in series, that tells me that all the charges that go through one have got to go through the other. The other way I can connect elements is in parallel. So here's a situation where now I have, say, current coming in, where my charges come into this junction. Some of them will go up through element 1. The rest will go down through element 2. All of them will recombine at this junction and then go out. So whatever charges went across element 1 couldn't have gone through element 2. And whatever charges went through element 2 couldn't have gone through element 1. So whether things are connected in series or in parallel is basically an issue of, do the charges have to go through both of them, or can the charges only go through one or the other? So if the current splits and then recombines after going through one or the other, those are connected in parallel. If the current has to go through one, then has to go through two, then those are connected in series. And so we'll see that how we choose to connect things within circuits will greatly affect what's going on within the circuit. So we want to become fairly comfortable fairly quickly in terms of recognizing how these things are being connected.